This example or examples in this video will follow up to what we had covered in class regarding proving trigonometric identities. So if we take a look at this one, in our third example, we have the cosine of x plus y multiplied by the cosine of x minus y, and that's equal to the square of cosine x plus the square of cosine y minus 1. So what we need to consider is which side of this statement we're going to work with in order to prove that it's an identity. Well, both sides do look equally heavy with expressions, right? They both have a considerable number of terms which might make it possible to work out or provide work on either side of the expression. Now, my mind, as yours might be at this point in time, leaping to something that looks very characteristic to us. There are expressions here to which we have expansions for, and namely it's these two here. Okay, so we do have expansions for the cosine of x plus y and the cosine of x minus y. So what you'll see on this slide, and maybe even on the next one, is simply a working out of the left-hand side. Just because of the length of the expression, there just won't be enough room on this particular page to provide that. So let's have a go at the left-hand side, and let's take the expression that we have and let it expand or provide the expansions. So the cosine of x plus y, if you were to check your formula sheet and or memory banks, this is equal to the cosine of x multiplied by the cosine of y. And from that, we're going to subtract sine x and sine y. Okay. This is being multiplied by expansion of cosine of x minus y, okay, which is virtually the same thing as what we've written down, except the difference is that there is an addition sign. Between these two products, cos x, cos y, and sine x, sine y. So moving forward, you can see that we actually have two binomials. So we have an expression, cos x, cos y minus sine x, sine y, that really is a two-term expression. Okay, so you can kind of see that here. We have one term, we have a second term, and over in the following bracket, we have a first term and a second term as well. So being that we have two binomials and we're multiplying, we're going to expand. Okay, so let's do some expanding. So if we consider expanding these two terms, what are we going to have? Well, we'll multiply our cosine x's together, and we'll have cos squared x, cos squared y. Okay. Now what we'll do is we'll take that very same term, and we will multiply that by the last term. So we'll have cos x, cos y. And that's positive, given the positive sign here. So cos x, cos y, okay, times, or multiplied by sine x, sine y. So now we're going to consider an inner product. So let's go with, let me change colors on that. So we're going to take this term here, and we're going to multiply it by this the term here. Notice the sign in this case is negative, right? You can see that here. So we'll have a negative term. So we have negative sine x sine y multiplied by cos x cos y. Okay, given that we're running out of space here, I'm going to drop down by using a brace, that is a square bracket, and we'll look at the final expansion. I'll choose a different color here. We're going to take the last term here and multiply it by this last term. Again, taking note of the signs, we have a positive and a negative, so the final sign will be negative, and we will have sine squared x, right, multiplied by sine squared y. Now the interesting thing about this is you heard me mention that we have two binomials. The only difference between them is the positive and the negative signs. So if you think back, we really do have a difference of two squares. And with a difference of two squares, what you should immediately recognize is that we have terms that are opposite. Okay, they have the same meaning, the same value, right? Because the multiplication, the order in which they're multiplied doesn't matter. They're exactly the same. So one will cancel the other. So what's nice about this is that the expression then tidies up as, oops, let's undo that. It is cos squared. And let's see here, we're having an issue with a smartboard in terms of its ability to write. Let's try that one more time. Okay, I think we're back in business now. Cos squared x cos squared y minus sine squared x sine squared y. So at this point in time, let's take a look back at the goal. Okay, let's take a look at that. What do we have? We have particular pieces here. We have cos squared x and we have a cos squared x here, which is helpful. We do have a cos squared y, but it's separated by an addition sign. So we need to consider perhaps eliminating these sine squareds, right? So let's see if we can't do that. So let's think about the following. Okay, I'm just going to extend the page a little bit. And let's consider Pythagorean identity. Right? Recall the Pythagorean identity. And we'll just go very general here. We'll just say that sine squared a plus cos squared a equals 1. I don't want to use x and y to complicate the situation here in case the x's and the y's don't happen to have the same values that I'm reporting here in this identity. So with that being said and written, we could do a substitution. In fact, what that implies, right, and using this particular rule, we could say that sine squared x is 1 minus cos squared x. We can also say that the other expression, sine squared y, would be 1 minus cos squared y. Okay, so therefore, what do we have now? Well, therefore, we can write the following. Let's leave this term alone, but let's open up a set of brackets here. Let's replace the sine squared x by 1 minus cos squared x. we'll replace the sine squared y by 1 minus cos squared y. I'm going to introduce a larger set of brackets just to go around this here to indicate that we'll do the expansion first. So we have a perfect square, 1 minus cos squared x, 1 minus cos squared y. So moving forward, let's do the expansion. So we'll have positive 1. We'll end up with minus cos squared x, okay, minus cos squared y, plus cos squared x, cos squared y. Okay, so moving forward, let's see now, choose a different color. This term stays. So let's deal with the expanding the negative into this bracket. So we'll have minus 1 positive cos squared x. Well, this is looking good if we remember back to our initial line. Positive cos squared y and negative cos squared x, cos squared y. So good news, you can see it, right? We have opposites, also known in math as additive inverses. So they will cancel. And lo and behold, we'll just continue as O Canada plays in the background. You're welcome to stand at attention while you complete the video lesson. And again, smartboard's acting up. Let's try this again. So reorganizing the terms that we have cos squared x plus cos squared y minus 1. Again, good news, if you look back to the top, in the right-hand side of the expression is exactly what we've come up with here at the bottom of the simplification of the left-hand side. So in conclusion, let's do that. So since the left side equals the right side, we can say that the cosine of x plus y came first. Yes, it did. Cosine of x plus y multiplied by the cosine of x minus y is equal to cos squared x plus cos squared y minus 1 for all values of x belonging to the real number system. Okay, so there should be no values that are undefined, as we're not dividing by any cosines, sines, or tangents where we would have undefined values. Okay. Last but not least, we do have one more. Okay, and I feel like I'm forgetting one thing. As per what we were doing in our lessons in class, we'll just write down the strategies. We used compound angle identities, we used the Pythagorean identity, and we used some expanding. Okay. Last but not least, there's one more example. We're going to prove that cosecant x divided by the cosine of x is equal to the tan of x plus the cotangent. So both sides have the same number of expressions. So we will probably deal with both sides one at a time. So the left-hand side is cosecant x divided by the cosine of x. Given cosecant x, do recall, okay, that it is equal to the reciprocal of sine. So we'd have 1 over sine x divided by, I'm going to go with a double bar to indicate a compound fraction, over cos x. So if we put that all together, multiplying by the reciprocal of cos x, we'd have 1 over sine x cos x. Okay. On the right-hand side, we have tan x and cotangent. Recall one of the ideas or rules for working with identities, trig identities, was to convert your signs using the quotient identity of sine over the cos of x. And the same thing applies to its reciprocal. Cotangent of x would be cos x over sine x. In this case, we have two fractions. Let's get a common denominator. We'll need a sine x and a cos x. The first numerator, that is sine x, will have to be made equivalent by multiplying it by sine x. So sine squared x. Well, in like manner, to balance out cosine of x in our denominator, we're going to have to square that. Okay. Well, what you can see now is the Pythagorean identity can be used. So using the Pythagorean identity, we can see that this will then be equal to 1 over sine x cos x. And in conclusion, we do have left side equal to right side. So since left side equals right side, cosecant x divided by the cosine of x is equal to tan x plus cotangent of x for all, let's get into some symbols here, for all x values belonging to the real number system. Okay, so if we go back and look at the strategies that were used, and every identity can have a different approach, which is why the more examples you do, the more thinking you put into it, the better we get at solving or proving trig identities. So here we used more than one trig ratio, a reciprocal identity, as well as the quotient identity for for tangent and cotangent. We also used a common denominator and some fraction skills to come up with our proof. Your next opportunity to learn is going to be found on the course website, so please check Unit 4, Trigonometric Functions, and the homework assignment that's posted there in the practice column, and that homework is drawn from your textbook.